Okay, welcome to my Lab 6 Magnetic Molasses by me. Okay, the purpose of this lab is to measure the effect of the magnetic force caused by a falling magnetic object through a conductive tube. This is that demo we've been doing in a lecture for the past 2 weeks where we drop a metal ball through a metal tube and it slows the fall significantly. Our goal was to measure that experimentally and then compare that to a computational model we made of that process. So the fundamental principles we used, you can't see that, but we're supposed to have Biot-Savart law up here. Don't know where that went. And then the magnetic field of a dipole, and then the flux of B equation. And that flux of B, the change in that flux of B is going to cause an electromagnetic current, which is going to cause another negative magnetic field to pop up that opposes that, and that's really going to form the basis of our physical interactions. So our system is going to be the tube and the bar magnet. We're starting the Earth, or going to be gravity and Earth's magnetic field. We're going to hope that Earth's magnetic field is not large enough to interfere right now with what we're doing. Relatively, the size of our magnetic field from our magnet and our tube should be greater than the size of the magnetic field from the Earth, so it shouldn't come into play in our results. So here's our experimental data. As you can see, on average, it took 1.46 seconds for our little bar magnet to fall all the way through the tube. So here's our code that we used to achieve this. As you can see, these are just the physical properties of our thing. And then we have dipole B, which is just the equation of a dipole with our mu and our r. And then here comes kind of the more interesting stuff. Here's d flux dt analytic, in which we calculate the change in magnetic field based on the speed at that time. We're going to do it analytically instead of by calculus because we have GlowScript and it's easier to do it that way. But as you can see, we have 3 times mu naught over 4 pi, which is just km, times 4 times pi times the magnitude of magnet dot mu, times the speed of that moment times the distance away from that ring times the radius of that ring squared. And that's all divided by 2 times the radius of the ring squared plus distance squared raised to the 5 halves. And this equation just for every ring in the tube. Also, we're going to say a tube is a collection of stacked rings, each with a thickness and a radius. And the radiuses are all the same. The radii, they're all the same. And then there's this while loop over here. We're going to do our calculations. Basically, we're going to drop the thing into the tube. It's going to go through the tube. As it goes through the tube, its speed increases. Its speed increases causes a change in magnetic flux. That change in magnetic flux causes a current with a restorative magnetic force which attempts to slow down the bar magnet. And as you can see here, for ring and tube, that's where we do that calculation. We calculate d flux dt. We then calculate the force on that ring, which is the absolute value of the current in the ring times 2 times pi times the radius of the ring times the magnitude of the B field out the ring times the sine. And if we dropped it correctly, it should be dropping straight down, so the sine of theta should just be 1. And we're going to add that to it's a for loop, we're going to add those all together. That's how we're going to get the magnitude F on the magnet. We're going to add that to the gravity to get our net magnetic force. At some point, they should equal 0, which is what we hope to see. And then we're going to do kinematics there to get our velocity and our position. So here's our computational model. As you can see, based on this graph, it falls at that increase in speed, then causes a magnetic force, and then it slows to a point where it's a constant. And then it gets to the end of the tube, and the magnetic force starts to go away, and it starts to fall again. But that's, as you can see, 1.43 seconds on average in our tube, and that's 0.03 seconds away from what we found our average to be in our experiment. So potential errors, we could have dropped the bar magnet and hit the edges, or we could have dropped it too fast and imparted an initial velocity. Our timing was done with an iPhone timer, which is imprecise due to the nature of iPhone timers. And our measurement was the width of the tube are imprecise because we just had a ruler, and it's a little bit hard to get, real sig figs with just a ruler beyond the 2 sig figs. So what we observed is that as the bar magnet fell, it slowed its fall through the tube, which is what we matched in our computational model. What if the resistivity of the conductor were reduced as close as possible to 0? As the resistivity reduced to 0, the current would go up to infinity because V equals IR, and then the force on the bar magnet would increase to the point where it couldn't fall. What if holes were slots got in the tube? Then the tube wouldn't be conductive, and the magnet would be unaffected by the two. Basically, it wouldn't do anything because current can't jump gaps. Okay, that's it. Thanks for watching my lab. Thank you.